Good day, my name is Megan Weyers and I'm currently a postgraduate student at the University of Pretoria in South Africa. I will be presenting on the effect of curing regime on the material properties of ultra-high performance fibre reinforced concrete. Despite the remarkable progress in the field of engineering in South Africa, it is still a developing country. Although there have been positive innovations in the research fields in recent years, the practical applications thereof remain a challenge. Therefore, development and design of practical and cost-effective mixture designs while incorporating readily available materials is of great importance. The curing regime significantly influences the microstructure and mechanical properties of any concrete, including ultra-high performance concrete, by increasing the rate of hydration, advanced the pozzolanic reactions, and also increasing the early age strength development. Various curing regimes or techniques are available. These kind of curing techniques are, however, expensive and unpractical to apply to bulk applications, which then limit the wider use of ultra-high performance concrete in South Africa. The application of heat curing raises a lot of questions regarding the negative effects thereof on the performance of ultra-high performance concrete components and their service life. Consequently, the focus of this study was to examine the effect of curing conditions on the material properties of ultra-high performance fibre reinforced concrete when using two different curing regimes, namely 25 degrees Celsius and 80 degrees Celsius water curing, especially with regards to using materials available in South Africa. A Class 1 52.5 R Portland cement with a relative density of 3.14 was used for the mixture. Local streams of waste materials, such as fly ash and silica fume, were chosen as cement extenders, not only for the economic benefits, but also to increase the workability and efficiency of the mixture, as well as the mechanical properties. 3 types of aggregate with different grain sizes were chosen to enhance the packing density, namely silica sand, dolomite sand, and crushed dolomite stone. Superplasticizer were added to improve the workability of the mixes. Straight steel fibers with a length of 13 mm and a diameter of 0.2 mm were used in all the mix designs. The particle size distribution of all the dry materials for the mixture can be seen in this figure. A laser and ultrasound test was conducted on 2 samples from each material, and the average of the results was calculated and plotted as the particle size distribution. Scanning electron microscope images of cement, fly ash, and silica fume can be seen in the top 3 images. All 3 images have a scale of 2 micrometers, and this can be seen in the left bottom corner of each image. The image of silica sand and dolomite sand used is shown in the 2 bottom images, and the scale of both images are 100 micrometers. Having a closer look at the undensified silica fume particles, with a scale of 200 nanometers, it is clear that agglomeration of the undensified silica fume particles is present. An optimum particle packing of granular ingredients of concrete is the key to a durable and sustainable concrete. It can result in a denser granular structure with enhanced mechanical properties and improved porosity. The concrete mixture design development in this study was based off of particle packing model theory. Looking at the equation used to calculate the well-known Fuller curve, this equation only considers maximum particle size, and it is recommended that a finite lower size limit is required to better present the finer particles. It was therefore decided to use the modified Andreasen and Andersen particle packing model to optimize the ultra-high performance concrete matrix. This method incorporates minimum particle size, and the range of fine particles is better presented. The mass proportion percentage of each individual material in the concrete mix was adjusted until the deviation between the target curve determined using the equation shown and the composed mix was minimized. The composition of the concrete was only then considered optimal. The grading curve for the composed mix is shown in the figure by the dotted line. The residual sum of squares obtained for the grading curve is 15.9 and the R-squared value is 0.97. The target curve as well as the Fuller curve is also shown by the solid line and the dashed line respectively. It can be seen that the finer particles are better represented by the target curve opposed to the Fuller curve. The composed mix then serves as the optimized ultra-high performance concrete matrix, which was used for the mixed compositions throughout the study. Response surface methodology was then used to optimize the combined fiber and superplasticizer content. Response surface methodology is a set of statistical and mathematical methods that assists in the analysis of responses that are influenced by several variables. It has a variety of response surface designs that can be used, and central composite design was used as the response surface design in this study to optimize the combined fiber and superplasticizer content. The three different types of points that define the region of interest are illustrated in the figure. The factorial points are positioned on the corner of the squares. The actual points are positioned a distance alpha away from the center point in the positive and negative direction, and the center point are positioned at the intersection of the two axes. The coded variables used is shown in the table. The response surface design has an improved quality of prediction when it is rotatable, which is influenced by the alpha and the number of center points. Fiber content was varied between 1% and 3%, while the superplasticizer content varied between 2% and 6% of the cement content. Each one of these points then represents a mix design. The central mix was cast 3 times to test the repeatability of the experiment, and the mixes were cast in random order. This led to 11 different mixture designs as shown in the table. A water cement ratio of 0.27 was kept constant throughout all the mixes, with about 550 kilograms per cube of cement extended with 17% fly ash and 17% silica fume. Relatively low cement content is used compared to other ultra-high performance concrete mixtures, which can go up to about 1,000 kilograms per cube. Coarse aggregate was also incorporated in the mixture design, which is not the norm for ultra-high performance concrete. The responses obtained from the central composite design were used to optimize the combination of fibers and superplasticizer to give the optimum performance in terms of acceptable mechanical properties. The criteria used to obtain the optimum performance is shown in the table. Considering the criteria, an overlay plot was drawn and is shown in the figure with the blue triangle. Any combination of fiber content and superplasticizer content can be chosen that falls inside the blue triangle, and an optimized mixture design can then be obtained. This led to the mixed design as shown previously. The casting procedure and curing method that was followed is shown in the diagram. After casting took place, a curing blanket was placed over all specimens in a temperature-controlled room for 1 day. After demolding took place, half of the specimens were placed in a 25 degrees Celsius water bath, while the other half of the specimens were placed in a different curing bath. To ensure that no thermal shocking took place, the water temperature for this bath was set to go up gradually from 25 degrees Celsius to 80 degrees Celsius. The specimens were left to cure for 48 hours. Thereafter, the temperature of the 80 degrees Celsius water bath was set back to 25 degrees Celsius. All the specimens were then left to cure at 25 degrees Celsius until the day of testing. Workability density, compressive strength, splitting tensile strength, and modulus of elasticity tests were performed. Workability was measured by using a flow table test, and the flowability was recorded as 310 millimeters. The limit between the linear elastic behavior and the ductile behavior of ultra-high performance concrete was determined by monitoring the transversal deformation perpendicular to the load direction during testing. 2 separate peak load conditions, namely the principal crack formation and the secondary crack formation, were thus determined during the splitting tensile strength test. The transversal deformation was measured with spring-loaded LVDTs, as can be seen in the figure. The average cube densities obtained are tabulated. The difference caused by curing conditions was deemed insignificant. This illustrates that thermal curing has no effect on cube density. The cube compressive strength was measured by testing 100 mm cubes, and the strength development over a period of 90 days is illustrated in the figure. The graph indicates that long-term strength development for concrete specimens is higher when cured at 25 degrees Celsius water than in the 80 degrees Celsius water. The cubes cured in the 25 degrees Celsius water show a gradual increase in strength up to 90 days. However, the cubes cured at 80 degrees Celsius reached a maximum strength of 157 MPa after 7 days. Thereafter, the strength slightly decreased up to 90 days. The modulus of elasticity results are shown in the table. The cylinders cured in the 80 degrees Celsius water yielded a slightly lower value compared to the cylinders cured in the 25 degrees Celsius water. However, a low standard deviation were obtained for both curing regimes. The stress deformation graph for the 28-day splitting tensile strength for the cylinders is shown in the figure. Two load peaks can be seen in all the results, with the first peak occurring with the initial or the first crack, and then a second peak forming as a result of the residual strength of the fibers. Although no significant difference can be observed in the initial cracking strength, the specimens cured under conventional curing conditions reached a higher secondary peak strength compared to the heat-cured samples. A higher variation in the secondary cracking strength for the specimens cured in the 25 degrees Celsius water was observed. Scanning electron microscope images from concrete samples is shown. The image was taken after 90 days of curing, and the scale for both images was 20 micrometers. Both images show the dense microstructure of ultra-high-performance fiber-reinforced concrete. Same images of unhydrated silica fume agglomeration on the left and an unhydrated flash particle on the right. Both these samples were taken from the inside of an ultra-high-performance concrete cube after 90 days of water curing. Unhydrated particles were observed in samples from both curing regimes. The scale on both images was 1 micrometer. In summary, a maximum cube strength was reached after 7 days for the heat-cured specimens, while specimens cured in the 25 degrees Celsius water showed a gradual increase in strength up to 90 days. The secondary peak strength, or splitting tensile strength, for the conventional cured specimens was higher than the heat-cured specimens. Consequently, it can be concluded that heat curing is not recommended when considering the long-term strength development. Thank you very much for listening. Please feel free to contact me with any questions.